In Lesson 4.5, Integration by Substitution, we're going to learn our first of quite a few special integration techniques. This one essentially involves undoing the chain rule. You remember back when we differentiated, the chain rule simply said that if we are differentiating a composite function, that we differentiate the outside part first, and then multiply that by the derivative of the inside part. Well, with this u-substitution that we're going to learn in this lesson, we're going to basically undo that. We're going to find what is the differentiated inner part, where's the differentiated outer part, and then throw it all together in an integral to come up with our original function. It'll be a lot of fun. It'll be a lot of excitement. But before we do any of that, let me set the stage with a quick differentiation problem that uses the chain rule. Let's take a look. So before we get into this substitution stuff that I've been talking about, let's go ahead and make up a differentiation problem. I'm going to make one up that looks something like this. Let's have 1 over 32 multiplied by, let's say, 4x squared plus 3. And let's take that quantity to the fourth power. And then just for fun, let's put a plus c on there. Now, if we wanted to differentiate this, of course, it wouldn't really be that bad. I could keep my 1 over 32. This 4 right here is actually going to drop down, and I'll have my 4x squared plus 3. Of course, now it'll just be to the third power. And then I will need to, of course, follow that up, because of the chain rule, with the derivative of this inside part right here, which in this case would just be 8x. Differentiating this plus c, because it's a constant, the derivative is 0, so I'm not even going to bother with that. But if I put all of this stuff together, take a look what I'm going to end up with here. The 8 and the 4 and the 32 are all going to cancel. I still have this x left over. So I have x multiplied by the quantity 4x squared plus 3, quantity cubed. All right, great. So there's a differentiation problem that involved the chain rule. Let's say that we had an integration problem based around this right here. Now that we know that this is the derivative, we know what the integral is going to be, but how do we get there? Well, to answer that, let's go ahead and take a look at example A. As you see, it actually is the integral of x times the quantity 4x squared plus 3 cubed. Well, that's exactly the result we got when we differentiated this, so we know what our answer is going to be. In fact, it's going to be that right there. But how do we get there? The easiest way to do this is with a technique called u-substitution. To show you u-substitution, all we need to do is create a u, which is going to be the internal part of some function in our integral. There'll always be something like a square root or a sine of something, or in this case, something cubed. That something is our u. So in this particular case, our u, or our inside part, is 4x squared plus 3. We also need to define the derivative of u, which usually isn't too bad. In this case, it's simply going to be 8x dx. No big deal. And now that we've done that, can we kind of reform our integral in a sense? I see that this is going to be u to the third power, and I have an x, but in order to have a du, I need 8x. So what I need to do is make my integral look like my u and du. How can I do this? Well, instead of just having x, how about I multiply an 8 in there? Am I allowed to do this? And of course you should say, well, no, of course you're not allowed to do that. You just multiplied the entire integral by 8. But if I go ahead and multiply it by 1/8 on the outside, have I convinced you that I've really made no difference now? Hopefully I have. The reason I've done that, of course, is so that now I can rewrite my integral as u to the third power. There's u to the third. And then right here, my 8x dx, well, that's du. So I can just actually substitute du in there. And now this is a very, very easy integral to do. I'll simply have 1/8, multiply that by, let's see here, u to the fourth over 4, and add my c. Now, I'm not really done because I don't want to leave this in terms of u. If I want to go ahead and substitute my u, which is right here, substitute that back in, well, look what I'm going to get. 1 over 32 multiplied by u, which is 4x squared plus 3, to the fourth. And then, of course, plus c. Now, that's quite interesting because that is the original function that I came up with to begin this problem. So, what am I trying to show you? When you have an integral that's not quite so easy to do, perhaps that's because there's an inside part to that integral and then some other fluff just hanging around. If that's the case, call that inside part u. Somehow force that fluff to look like a du, and then you can integrate no problem. Before we move on to any other examples, though, let's go ahead and formalize this real quick by taking a look at the boxes on the right side of your notes. After we formalize it, we'll go ahead and move on to example B and C, see more examples of how and why this works. So before we do any more examples, I do want to formalize this u-substitution stuff so that as we go through the remainder of the examples, you can look back at these boxes and kind of see how it all works together. It's a little bit confusing because when you look at this, if we want the integral of f of g of x multiplied by the derivative of g of x, that just looks like a whole bunch of garbage. But think of it as inside and outside functions. We're integrating some outside function that includes that inside part, and then there's the derivative of that inside part. That's the chain rule. And what we're going to end up with overall is the antiderivative of f of g of x. And then, of course, don't forget your plus c. That's your constant of integration, and that must always be there if you're doing an indefinite integral. So there you go. This is just to generalize it, or maybe make it a little bit easier to look at instead of all these f's and g's. If we have the integral of some function f of u, where u itself is some function, and then we have du, which is the derivative of the inside part, well, what we end up with is capital F of u, plus c, of course. So, just remember that. F of u plus c comes from the f of u du. The difficult part here is getting our integral to look like this. This du is often quite a challenge to obtain, but most of the time it's not really too bad. It's just multiplying by some constant and multiplying by the inverse of that constant out front of the integral, just so there's that balance and harmony. So that's the whole idea behind it. So here's the general power rule. This is just if we have some function raised to some power multiplied by the derivative of that function. What are we going to end up with? Well, of course, it's just going to be that function, g of x, but it'll be raised to the n plus 1 power and divided by n plus 1. Again, don't forget your c. So where did all that n plus 1 come from? Just remember the basics. Don't ever forget the basics of integration, at least. Whatever the power is, it's plus 1, and we divide by that. So if we have the integral of u to the nth power, well, that's simply going to be u to the n plus 1 divided by n plus 1, and then plus c. Again, the hard part is going to be making this du happen, but therein lies the challenge, and that's what we'll be focusing a lot of power on as we go throughout these notes this lesson here. So, with all that being done, let's go ahead, take a look at example B, and see how this thing works out with our new u-substitution method. As we take a look at example B, can you kind of discern where the internal function is? You see we have x cubed on the top, and that's fine, that is as it is. But on the bottom we have the square root of 1 plus x to the fourth. The square root of not just x, but the square root of some function. Well, that function right there is what our u is going to be in this example. So, I'm just going to write out to the side that u is 1 plus x to the fourth. And by doing that, we can differentiate that and find out that u, or rather du, is actually 4x cubed dx. Where did that come from? I simply differentiated u to get du, and there it is. So now that I have that, perhaps I can rewrite this function. Let's see, I clearly have a square root of u in the denominator, but do I have du anywhere? I need 4x cubed, and I certainly don't have 4x cubed. Well, close enough though. I do have x cubed, and what I could do is just multiply that by 4. so long as I throw a 1/4 on the outside. Harmony and balance, they're both there, and everything is good. And now I can go ahead and rewrite this thing. Looks like I'm going to have a square root of u in the denominator, which I'm going to rewrite as u to the negative 1/2. And now I do have du, 4x cubed dx, and there it is, 4x cubed dx. So my integral turns into 1/4 the integral of something very, very easy to work with. In fact, if I do this, let's see, the integral of u to the negative 1/2, well, that's simply 2u to the positive 1/2. And I'll just add c to that. And I'm not done yet. I do need to substitute my u back in so that I'm in terms of x. And if I do that, I'm simply going to get 1/2. Here's u, 1 plus x to the 4th. And that'll be to the 1/2 power plus c. Of course, if I want to, I can turn that 1/2 power into a square root. And then I'll have that answer that would probably be the answer on your multiple choice test. But on a free response, these two are exactly the same, and both would be correct. So, is this true? Is the integral of this thing up here really that thing down there? Just to check, let's go ahead and differentiate. This is the fun part. This is making sure that everything really worked. So the derivative of 1/2 multiplied by 1 plus x to the 4th to the 1/2 power plus c. That's my final answer that I got. Well, if I differentiate this, let's see here. I'll have 1/2, and then this 1/2 will come down. I'll have 1 plus x to the 4th. To what power? Well, if I drop 1/2 by 1, that'll give me negative 1/2 power. And, of course, the c is essentially gone. So, let me work this out. It looks like I'll have, oh, wait a minute. I forgot something, didn't I? Gotta be very careful. I forgot the chain rule. And the chain rule is going to be the derivative of this inside part, which is 4x cubed. So now let me go ahead and put this all together. These two 1/2s give me 1/4. And this 4 over there actually gives me 4/4. I do have my x cubed, and then I have 1 plus x to the 4th to the negative 1/2 power. And if I simplify that a little bit, maybe not simplify, but simply rewrite it, it would be x cubed all over the square root of 1 plus x to the 4th. And notice that is exactly where we started. Our result is correct. So all this being done, let's go ahead and take a look at example C, where we're not just going to do a u-substitution, we're actually going to find the value of this definite integral. I'll show you how it works. There's a shortcut and a long way. Both work, both are cool. Let's see them now. So here in example C, we do have a definite integral. Notice that we have lower bounds of 8 and an upper bound of 12. And so we're not just going to find some function that this integrates to, we're actually going to find a value. But if we go ahead and take a look at it right now, we're not going too far until we figure out what kind of substitutions to make. In this one, hopefully you should recognize that u is going to have to be the internal part of the square root function. So I'll have x squared minus 8x plus 1. And of course that implies that du will be 2x minus 8 dx. So clearly we have the square root of u in the denominator. Du is 2x minus 8, and we don't have 2x minus 8 anywhere in this problem. But if you look carefully enough, you'll notice that if we simply multiply the numerator by 2, that would give us 2x minus 8. And we can do that so long as we balance it with a 1/2 on the outside. Great. So how is this all going to look? I can change this into 1/2. I'll have the integral, again, from 8 to 12. I'll have u to the negative 1/2. That's on the denominator there. And then I'll just have du on the top. Remember, du is 2x minus 8. And that's exactly what I have here after I multiply it by the 2. So what can I do with this now? Well, I can integrate it, of course. Keep my 1/2 on the outside. This u to the negative 1/2 is going to turn into 2u to the positive 1/2, and I'll need to integrate that from 8 to 12. Well, herein lies a problem. While I can cancel the 2 and the half, I can't plug these into the u, because both of these bounds are in terms of x from the original problem. So that's no problem. All I really need to do is just put my u substitution backwards. So what I'll actually have is the square root of u. And this is why we always write down what u is before we jump into the problem. So I can always refer back and say, u to the 1/2, that's the square root of u. And if we evaluate that from 8 to 12, it's really just arithmetic from here. If you run 12 through 144 minus 96 plus 1, that gives us 49. Square root of 49 is, of course, 7. And then run the 8 through 64 minus 64 plus 1. Square root of 1 is 1. And so it looks like we're going to end up with 6 as our final answer here. Now, hopefully that wasn't too difficult. It was simply turning everything into u, doing the integration, turning it back into x, and then substituting our lower and upper bounds as per the fundamental theorem of calculus. But there is a shortcut. Check this out. When we rewrote our integral, we wrote 1/2 the integral, and we did u to the negative 1/2 du. But we left both of our bounds, the 8 and the 12, both in terms of x. Check this out. Since we turned the function into a u, wouldn't it be logical that we could turn the bounds into u's as well? And we actually can do that. Since we know that u equals x squared minus 8x plus 1, what would u be if x is 8? And clearly, if you run 8 through the u equation, 64 minus 64 plus 1, we get 1 as our lower bound in terms of u. And if we do it with the 12 on top, well, what we'll get then, 144 minus 96 plus 1, that's actually going to be 49. So it looks like we just made things worse. Instead of 8 and 12, we now have 1 and 49. Looks hideous, but watch what's going to happen here. Now that everything is in terms of u, there are no x's left in this problem at all. Watch this. We'll have 1/2 multiplied by 2u to the 1/2, and we're going to integrate that from 1 to 49. Now, just as before, the 2 and the half cancel, but what we're left with here is just the square root of u. And since our bounds are in terms of u, it's nothing more than the square root of 49 minus the square root of 1, which again gives us 6. So now you're asking, what's the difference? We got the same answer. Well, of course we got the same answer. It's the same problem. But in one method, we went ahead and plugged our x's back in because our bounds were in terms of x. Sometimes that's a pain, having to go into u, integrate, then go back into x. If that's too much of a pain, you can just turn your bounds into u's as well. Notice our bounds here turned into 1 and 49, and we never had to switch back into x mode. It's your choice which way to do it. Both ways work. Both ways are equally acceptable. Just oftentimes, one way is quicker than another. It's your choice. And with that, let's go ahead and take a look at something new and exciting. These are called slope fields, and they bring a whole new level of enjoyment to calculus. Let's take a look now at example D. So, welcome to slope fields. What you see in front of you here on example D is a graph showing a bunch of little pieces of slope. Little pieces of slope. What do I mean by that? Well, all of these are solutions to a differential equation that's given in the problem there. You can see it yourself. But if I plug in any x comma y into that differential equation, what I'll get is dy dx. And what is dy dx? Well, of course, that's the rate of change of y with respect to x, or, if you like, rise over run, slope. And so no matter what x or what y I have, I can simply put them into this equation. It'll tell me the slope. For example, plug in the point 0, 1. 0, 1 is a point right here on the slope field. And if you plug 0, 1 into this differential, what do you get for dy dx? Well, clearly, you get 0. And what that means is that the slope of or rather the rate of change of a function, or the slope of a tangent line at this point, is simply going to be 0. And so what we've done is put a little piece of slope with a slope of 0. And that's how the whole thing works. If I wanted to put in a point, say 2, 0, into this differential equation here, look what I'd get for my slope there. Again, 2, 0. What would I get? Well, my slope would be 9 over the square root of 29. And 9 over the square root of 29, that's a pretty big slope. And so I've drawn that here. That's all the slope field is. A lot of pieces of slope that all represent solutions to this differential equation. How could all of these represent solutions? Well, think about what happens when we integrate. You remember that plus c? You remember that? Well, depending on what c is going to tell us where on the graph the function is. And so what the directions want us to do is to simply draw two functions on the slope field that could be representative of the family of solutions to this. Well, since I've already started a little piece right here, let me go ahead and continue that. If I go backwards, it might look something like that. And if I go forwards, probably something like that. How did that happen? Easily. I just followed the pieces of slope. Wherever they told me to go, that's where I went. Take a look at this one here. It looks like it's going up right here. And going to the left, it looks like I'm going down, kind of evening out, and then going down again. So there are two solutions to this differential equation. What the problem is now asking me to do is to find the actual solution, or rather the particular solution, that passes through this blue point right here. So I'm looking for the equation, essentially, of something like that. And that may or may not be correct. In fact, we're going to find that it's not correct at all. Maybe it should go more like this. Actually, I'm not going to be able to here. But let's go ahead and we'll mess with this differential equation until we come up with an equation that passes through this point. How is it going to look? Well, I have dy dx, and that's not really what I want. What I really want is just dy, and I'll show you why in just a moment. But if I multiply both sides by dx, this is what I'll get on the right side of that differential equation. And there's my dx. Why did I do that? Because now I can go ahead and simply integrate both sides. There's my integral on the right and my integral on the left. Now it's clear what's going to happen on the left here. The integral of dy is simply y. That was easy. Over here, this looks like a u-substitution problem, and of course it is. U will be x cubed plus 2. Let's let du be 3x squared dx. And now I can make my necessary tweaks to this. I do have the square root of u in the denominator, but to make du happen, I need 3x squared and dx. Well, I have dx, and I have x squared, but of course I do need that 3. So I'll stick a 3 right there, and a 1/3 on the outside. Now I can rewrite this integral. This isn't going to be too bad. It'll be 1/3 times the integral of u to the negative 1/2 du. And I know I've been rewriting a lot of integrals as u to the negative 1/2 du, but every problem is different, and you'll see that when you get to the assignments. So y equals all this stuff here. Looks like all I need to do is go ahead and integrate on the right side. And if I do that, I'll get 1/3. This u to the negative 1/2 will turn into 2u to the 1/2, and then my plus c, of course. So let me go ahead and rewrite this in terms of x. And here's what I'm going to have. 2/3 times the square root of x, rather the square root of u. There's u right there. So that'll be x cubed plus 2, and then my plus c. Am I done? Can I type this function into my calculator and get a graph that looks like this passing through this point right here? Well, of course not, because of that plus c. So what I need to do now is evaluate y at the point, the cubic root of 7, 1. I got that from the problem. That's right there. So if I do that, well, what's going to happen? Y turns into 1. So let's see here. Y turns into 1. On the right side, I have 2/3 multiplied by the square root of x cubed plus 2. Notice what x is. X is the cube root of 7. That cubed gives me 7, and then plus 2 plus c. Well, do a little handiwork here, and I think what you'll find out is that c actually equals -1. And what does that mean? That means that my final answer, if I plug that c into this function right here, what I will get is that y equals 2/3 times the square root of x cubed plus 2 minus 1. Go ahead and run that function through your graphing calculator. See if it doesn't look a lot like this, what we have on the slope field. Of course, I didn't get this exactly correct because it looks like the y-intercept is at -1. So somehow it should have gone down that way. But these are only approximate solutions. Now that we've gone ahead and integrated the whole thing, we have the actual solution that we call the particular solution. It goes through that particular point, and with that, we will revisit slope fields at a later time. Let's go ahead and move on to example D, back to the grind. Good times. Here in example E, we're going to evaluate another definite integral, very similar to the way we did back in example C. That being said, you should pause the video and try this problem on your own. You can do it the long way, like we did in example C, or if you prefer, you could do the shortcut, like what we did in example C. Either way, if you do it correctly, you will get the same answer. So pause the video, give it a shot, come back when you're ready to see the solution. Alright, so hopefully you've tried it yourself now, and you realize that in order to do this problem, we needed to u-substitute. There's a function inside of the square root. And so what we're going to do is call u that function. U will be 2x plus 1, which implies that du is simply going to be 2 dx. That makes this look a lot easier than those other problems we did. There's no x or x squared or anything wacky for our du, but we need a 2 dx in the integral. And right now all we have is a 5 and a dx. How do we handle that problem? Well, I'm simply going to take the 5 and move it outside of the integral. It's a constant. I can move it. It's all good. And what I need there is a 2. So I'm going to go ahead and put a 2 there now, which I'll balance by dividing this 5 by a 2 on the outside. That's awesome. Now what I can do is rewrite this integral as 5 halves times the integral from negative 1/2 to 4. This is u to the 1/2. And because I stuck that 2 in there, I can now write du. Perfect. Awesome. So let's go ahead and integrate this now. Let's first be aware that this is the long method. Notice we didn't change our bounds. So everything is going to have to end up in terms of x at the end. So let's see what's going to happen here. We'll have this 5 halves hanging out on the outside. When I integrate u to the 1/2, what I'm going to end up with is 2/3 u to the 3 halves. That will be integrated from negative 1/2 up to 4. And, well, let's see here. The 2's are going to cancel out. And so what I'll end up with is 5/3. Of course, I do need to plug my u back in. So this will say 2x plus 1 to the 3 halves power. And again, that will be from negative 1/2 up to 4. All right, we're almost done here. Almost done. All we need to do at this stage, keep our 5/3. If we plug our 4 into this thing, of course, we'll get 9 to the 3 halves power, which is 27. And if we plug negative 1/2 into this, that, of course, gives us 0. And 0 to the 3 halves is just 0. So it looks like we end up with overall 5/3 of 27, which, of course, is just 45. Now, that was the long way. If that's the way you did it and you got 45, excellent. You're looking good. You're doing great. Go ahead, move on to example E. See how that one works for you. However, if you tried the shortcut, then you're with me. Let's see how I did this. I started with 5 halves times the integral of u to the 1/2 du, just like the long way people did. But the bounds I changed. The negative 1/2, when I run that through my u formula, actually ends up giving me 0. And when I run 4 through my same u formula, that's going to give me 9. So let's see if that really helps a whole lot. Again, I'll have 5 halves multiplied by 2/3 u to the 3 halves, so nothing has really changed yet. But watch this. The 2's cancel out. I'm left with 5/3, but I don't need to change my u. Since my bounds are now in terms of u, I can just plug them in. 9 to the 3 halves, that's 27. 0 to the 3 halves, that's 0. And now I get my answer this way, again, of 45. Did you use the shortcut? It is a little bit easier, but it does involve changing those bounds. So it doesn't matter which way you do it, the long way or the short way. Just remember to complete all your steps to make the process correct. All right, well, our last example is not a definite integral, so we don't need to worry about this long way, short way thing. Let's just go ahead and integrate a very seemingly easy problem. Let's take a look at example E now. So our last example, example F, is a very, very interesting problem. Not a very difficult one, but the question is, if we have the integral of sine x times cosine x dx, what are you going to choose for u? It's really your choice. Quite honestly, I've done this problem both ways. Perhaps you would like u to equal sine x, and therefore du would be cosine x dx. If you want to try it that way, go for it. See how it works. But perhaps you would like u to equal cosine x. Maybe you're one of those people. Well, if that's the case, your du will be negative sine x dx. And if that's the case, I certainly invite you to give this a shot. I'll do it both ways. Well, I've already done it both ways myself, but let's try it here. If we do it the blue way, what we'll end up with is quite simply u du, which when we integrate is just going to be 1/2 u squared plus c. All right, no problem. 1/2 u squared plus c. If we work that out, that's actually going to be 1/2 times sine squared x plus c. Just to see that that works, go ahead and differentiate it. You might even be able to do that in your head. Remember, sine squared x, instead of thinking about it as sine squared x, you may prefer to think about it as quantity sine x squared. Of course, that 2 is going to come down, cancel out the 1/2, and we're left with just 1 sine x. And then by the chain rule, of course, we'd have cosine x, and the c is gone. So it looks like it works. But what if you wanted to try it the red way? Well, the red way wouldn't actually work right off the bat. We would have sine x cosine x dx, but for du would be sine x dx, but we need a negative sign in there. And so what I could do is just put the negative there, as long as I balance it outside. Now I can turn this into negative integral of u du, and of course that will lead us to negative 1/2 u squared plus c, giving us a final answer of negative 1/2 cosine squared x plus c. You can see that the answer is very similar whether we go with the red or the blue, but try differentiating both of them and see what happens. It might be interesting that the same derivative can yield quite interesting integrals. Very interesting to think about. All right, so here in lesson 4.5, we've covered some very, very, very important things that will persist for the remainder of this course. The idea of u-substitution will come up over and over and over again, all the way through to the end. If you don't get the u-substitution idea, you're kind of in trouble for the whole rest of the year. So remember, the whole purpose of u-substitution is simply to undo the chain rule. The chain rule a lot of people forget to do when they differentiate. In fact, you saw me almost forget to do it. But the chain rule is extremely important. And the way that we undo the chain rule is with u-substitution. A lot of people have trouble deciding what is u and what is du. Well, if there's a square root or an exponent or something like that, the part that's inside, the inside function, that is what you should write as u. And then du, of course, just follows from differentiating whatever you said u equals. So you don't need to look back at the integral to find out what du is. It just comes from u. Once we have that, we need to rewrite our integral in such a way that it's composed of those u's and a du that you specified. A lot of times that might involve a negative sign or a constant being multiplied. Things like that are the general case scenarios. Once you have the integral rewritten, then integrate. Of course, everything's in terms of u now because we have that du in there. But once we integrate and come up with our final, we can go ahead and unsubstitute that u, write the x thing back in for u, and that will yield your final results. Of course, remember, if it's an indefinite integral, put your plus c. Always put your plus c. Well, if it's a definite integral, however, we also u-substituted that, and once we u-substituted, we did everything pretty much the same, but when we got to the end of the problem, we had to plug in our bounds as per the fundamental theorem of calculus. That's really no big deal, but remember, there was the long way to do it, where everything stays in terms of x, and we turn it into u and then back into x before we do the fundamental theorem, or there was that shortcut where we turn the bounds into bounds in terms of u, and it just made things a little bit easier to deal with. It's your choice how you do it, of course. And then finally, we did look at slope fields in this lesson. We had a brief introduction to slope fields, I should say. And slope fields simply represent the family of functions that are all solutions to a differential equation. Differential equation simply tells us slope at any point on the coordinate plane. So really all the slope field is a bunch of little pieces of slope all over the place. And we can follow those to make a smooth curve, but to find the particular solution going through a point, we do have to do the u-substitution. We need to plug the x and y into our final thing to find out what c is, and then we have our final answer. So it's a lot of stuff, but it's very important stuff. So be very diligent as you're working on this assignment, and as always, good luck.